Alrighty, everybody. Welcome to Civic Tech YYC. It is December 12th here of 2023. Tonight, our feature is how the second quantum revolution will impact the economy. We're featuring experimental quantum physicist Katanya and educator AJ Sikora and their organization Qubo Consulting Corp. Just to get us started with a land acknowledgement, CivicTechYYC is an organization that resides on the traditional territories of the peoples of the Treaty 7 region in southern Alberta, which includes the Blackfoot Nation tribes of the Siksika, the Piikani, the Kainai, the Stoney Nakoda First Nations tribes of the Chiniki, Bearspaw, Wesley, and Tsuut'ina First Nation, and this is also homeland to the Northwest Métis and to the Métis Nations of Alberta. Civic Tech is a movement of the use of technology for public good. So we use data to design and address challenges that citizens and governments are facing to help citizens and governments work together to use that technology in data and design, pursuing opportunities for greater citizen engagement and more effective services, and growing the public engagement to enhance digital services in ways that are more inclusive, responsive, innovative, and open-centered. Civic Tech is a global movement that's expanded drastically over the last 15 years with the help of organizations like Code for All. In US, cities like Chicago, Boston, New York City have led the civic tech movement, and also other important national organizations such as Code for America, the US Digital Service, and 18F. There are civic tech organizations in many locations across Canada that are listed on the Code for Canada website, and also government agencies like the Canadian Digital Service. Civic Tech YYC was launched in 2017 by bringing together people who had an interest in improving their community through technology by leveraging the support of the City of Calgary and the Rainforest Network. And the driving force has been to break down the barriers between sector silos and create a space for collaboration, addressing the challenges and opportunities of citizens and government. As you can see on the diagram on the right there, the civic tech community sits in the middle of the City of Calgary and digital strategies, citizens and communities and social innovation, technology industries and alliances, as well as entrepreneurs, startups, and the research and knowledge basis. Data in the social sector has been rapidly expanding, and the amount and importance of the data has been increasing, and organizations are trying to leverage the power of that data for decision making, although many organizations lack the resources to collect and understand and use that data to make better decisions. And data professionals with the skill and knowledge want to become more engaged. So here at CivicTech, we promote volunteer projects and facilitate connections to make these technology for good projects happen. So just looking at data-informed learning, what we're doing is we're taking that data, and then from that, we go up the knowledge pyramid and we turn that data into information. By analyzing that information, we create knowledge, and through that knowledge, we create the wisdom. Just looking at some of our projects, there's the Budlib project, which is the library database management project that we have going on. We've tested on and off with different blockchain experiments over the years, just testing different ways to leverage blockchain for good. And Alice Lamb started her app here through Civic Tech called Volley, which you can find at volleyapp.com, which helps promote volunteers with organizations in the region here. We've also helped out with civic user testing groups, which are grassroots groups that facilitate better and more inclusive usability testing that engages residents in the creation of technology that's meant to serve them. And it's a concept that started in Chicago and is spread across to many cities, including Toronto's GRIP program, and now is here in Calgary with Inclusity. So we've helped to start Inclusity Calgary. It's a team of technologists, designers, public employees, and community organizers, entrepreneurs, and policy analysts, as well as other engaged citizens, with a shared vision that Calgary can be a more accessible city for all. The mission is to plan and design and run testing sessions with an inclusive and representative group of Calgarians to improve the usability of products, processes, and services for the public, private, and not-for-profit sectors. We are proudly supported by the Calgary Foundation, and it was created in partnership with Calgary UX. There's also our other partner organizations and groups within the ecosystem that we welcome you to check out. Code for Canada that helps sponsor and work with CivicTechYYC, as well as the other Civic Techs, Calgary UX, Data for Good, Rainforest Alberta that helps start us. There's also the YYC Data Society, Platform Calgary that supports the ecosystem. And for immigrants, we're also partnered with the Immigrant Techies Alberta group. Just if you want to keep in contact with Civic Tech on our social channels, there's the meetup page. We've got our website, X, formerly Twitter, still same handle, still same social media site for the most part. Instagram, started Threads now because that's really easy when you already have an Instagram account. So we'll be posting a little bit on there. LinkedIn, probably one of the best places to still connect with us. And we do have the Facebook that was started up recently. I will just open it up and we can talk about this after the main presentation, but I just wanted to check if anyone had any projects and or pitch ideas. If you want to just drop any of those pitch ideas in the chat after we're done the Q&A here tonight, we can address and talk about those and people can kind of make their pitch for the projects. But if you want to just add into the chat there, any interesting project ideas that you might have, we would really appreciate those. I'd like to just introduce our speakers here now. So Katanya and AJ, here's just a little bit of background on them as well. I think AJ and Katanya, do you want to introduce yourselves? And I'll just pull down this slide after you're done doing quick intros there.
Sure. Thanks, Ross. Do you want to start, Katanya?
Sure. So hello, everyone. My name is Katanya Kuntz. I'm co-founder and CEO of Qubo Consulting Corp, which is this lovely banner you see behind us. I'm also a research associate at the Institute for Quantum Computing, IQC, at University of Waterloo. And my main role there is the KeySat Science Team Coordinator for Canada's first quantum satellite mission. And KeySat stands for the Quantum Encryption and Science Satellite. So I have a PhD in electrical engineering, specializing in quantum optics, and a bachelor's of science in physics.
And hi, everybody. I'm AJ Sikora. I'm the other co-founder of Qubo Consulting Corp, and I'm also the Chief Learning Officer. I'm an educator and a businessman. I like to call myself an edupreneur. And I have over 10 years experience in teaching and coaching. My specialty is making education interesting and meaningful while focusing on the key information and how it relates to the stakeholders. I have a Bachelor of Management in International Management from U of L, and I also have a Bachelor of Education, which is also from University of Lethbridge.
Okay, thank you so much for the introductions there. And I believe you have your presentation there ready to go as well.
I'm ready to go.
Okay. Perfect.
Let's go back. Okay. Just wanted to make sure we didn't have the Apple bar at the top of the screen there. Okay, so thank you so much, Ross. We really appreciate you giving us the opportunity, and thank you to CivicTechYYC and all the volunteers. So once again, I'm AJ Sikora, and this is going to be called How the Second Quantum Revolution Will Impact the Economy. So in this presentation, we'll talk about quantum applications and try to demystify some of the hype. Okay, but before we begin, I want to talk about what this presentation is not. So robot butlers, doom and gloom, and tin hats are not in this presentation. Okay, so you might be wondering, why should I pay attention to quantum? So there are a number of reasons to start paying attention to quantum now. The technologies being produced will have various impacts throughout the economy. Businesses can utilize these new technologies to gain a competitive advantage. There is a threat, though, that quantum computers could break current encryption standards, exposing sensitive data. There is a quantum solution that can protect sensitive data from that quantum threat. And then also workers will be needed to transition to the newly forming quantum industry so that there will be lots of career opportunities opening up. So how can quantum impact the economy? My part of the talk will focus on these three aspects: the quantum threat, that's the threat of quantum computing breaking RSA, elliptical curve, or other forms of encryption. Luckily, there is a quantum solution known as quantum key distribution to thwart the quantum threat. As well, researchers and entrepreneurs are developing many novel business solutions. And finally, we will look at the quantum workforce and the need to upskill workers from various backgrounds to join the quantum industry. Okay, so the quantum threat. Why are quantum computers more powerful than classical computers? It's in their design. They use qubits instead of bits. Bits can be either a 0 or a 1, while qubits can be in a superposition state of 0 and 1 at the same time. They are also capable of parallel processing, which means that in some systems, all qubits can communicate with all other qubits simultaneously. It is expected that a quantum computing system will reach a sufficient level of computational power to break current encryption standards in about 5 to 15 years. There's a name that some people in the industry are using for this, and it's called Q-Day. Another issue for the quantum threat is that bad actors could be hacking encrypted data and storing it so that when a functional quantum computer is available, they can access that data. This is called harvest now, decrypt later. This is an issue for organizations that have a long lifespan on sensitive data. One thing to be aware of is the hype surrounding this. You might hear that Q-Day is coming soon and everyone is, getting ready for this, but the general consensus is around 5 to 15 years. Also, quantum computers can't do everything, and they can't do everything better than classical. And Katanya will speak more about this later. Okay, so let's look at quantum solutions. So in the quantum industry, the following technologies are being developed: computing, optimization, simulation, communication, and sensing. Next, I will talk about some of the exciting things that quantum technology could do. And so just so you're aware, the timeline is variable for these. It depends on the technology and the level of investment and business interest. Okay, so the first industry we're going to look at is data security. Because of the quantum threat, governments would not want confidential, encrypted communications being stolen by foreign governments or cyber criminals. Organizations, such as businesses, might hold data, such as health data, that would still be valuable 10 years down the road. One thing for organizations to keep in mind is the transition time it would take to implement new encryption standards for legacy systems. If it takes 20 years to implement a new system, it's not ridiculous to say that they need to start planning now. There are solutions to these issues, though, such as post-quantum cryptography, which uses more complicated math, which is difficult for classical as well as quantum computers to break. People expect that post-quantum cryptography will extend the time it takes for a quantum threat to break it. This is a classical solution and does not require quantum technology. However, it is vulnerable to attacks, as proven by the recent attack on one of the NIST candidates. A quantum solution to this threat is quantum key distribution. This is a theoretically secure form of communication that cannot be hacked by quantum nor classical computers. And Katanya will talk about this a little bit more later on as well. Now let's look at manufacturing. Using quantum systems to simulate real-world scenarios is known as quantum simulation. Utilizing this technology could improve the discovery of new materials for health sciences or manufacturing. The simulations can find materials that exhibit desirable traits and properties for various situations. Additionally, quantum optimization should be able to produce better results than the most efficient, high-powered computers of today. Optimization could improve the efficiency of production, logistics, and supply chain to produce more with less in less time. At the present, I've heard of quantum hybrid optimizations producing about the same or slightly better results in terms of efficiency, And in some cases, they produce the results much more quickly than classical optimization. Okay, let's look at healthcare. Quantum has a lot of applicable uses for the healthcare industry. Utilizing quantum simulation can help with drug discovery, much like the new materials discovery I mentioned on the last slide. Using quantum properties and sensing technologies can yield more precise and accurate data, which could improve diagnostics. Patients could benefit from using quantum optimization in treatment plans and analyzing test results, which could free up resources like doctors. Once again, the data security is an issue, as health information is the most expensive data traded on the black market. How can quantum technologies impact the travel, transportation, and logistics industry? They could improve fuel efficiency and route optimization. This could be used in planes, trains, boats, automobiles. As well, quantum sensors could improve the safety and navigation of all modes of transportation. Finally, let's look at finance. There are lots of investment opportunities with plenty of quantum startups looking to raise funds to grow their business. Also achievable with quantum optimization are financial modeling and portfolio optimization. There are a few companies that do this now, and at the present, there might be a slight advantage to use quantum optimizations, but as the technology evolves and progresses, it's expected that quantum's advantage over classical will grow. Now let's look at the quantum workforce. In order to grow this industry, there is a demand for highly qualified personnel. Right now, there are PhD and master's programs being offered by universities. And actually, at the University of Calgary next semester, they're starting a professional master's in quantum computing. And that's going to be their first semester of offering that program. There is also a need to upskill existing workers in other industries and bring them into the quantum workforce. At some point in the future, we might have plans to offer upskilling courses too. So which backgrounds should be upskilled? Well, the quantum industry has many applications. So many different backgrounds will be necessary, some of which are physics, mathematics, all types of engineering, chemistry, actually I would say all types of scientists, computer science, and tradespeople. Keep in mind that this is not an all-inclusive list. If you have a different background and want to transition into the quantum industry, do some research to find out how to transition. And I'm just going to leave that slide. We'll summarize everything all at the end here. So next we have Dr. Katanya Kuntz, who's going to present on what is quantum.
Okay. Hello, everyone. So yes, I'm Katanya. And now, what is quantum? So quantum physics is the study of the microscopic, the submicroscopic atoms, and smaller than atoms, the elementary particles that are inside atoms. Quantum physics explains how molecules are formed, how chemical bonds work. You can see in this image here on the left, these are some examples of different types of molecules. And so for quantum physics, we have a model that mathematically describes the quantum world. These models have evolved as we learned more about what is happening inside atoms and inside molecules through experiments. And as I mentioned, I'm an experimental quantum physicist, so I like to think of things in terms of real world, tangible concepts. So here you have some of the pictures of the model of the atom. So Rutherford model in the middle here, that was one of the original ideas where we have a nucleus in the center and then electrons orbiting around. But there were some flaws with this concept. And so Bohr model of the atom was developed, which had these electron shells where the electrons could hang out and not worry about having to spend energy being at those energy levels. And then from there, we've developed now this quantum mechanical model of the atom. And so on the bottom left here, you see the hydrogen wave function. So now the electrons are seen as probability clouds around the nucleus, and the different energy orbitals have these different shapes. The quantum world is clearly very different from the classical world. As you can see from this picture here of what chalk looks like at the bottom right here on the screen, this is what a microscopic image of what chalk looks like. So it's that you would write on a blackboard. So it's very different from what we see in our physical world. So now I think we understand what is quantum on a basic level. So now what is this quantum 2.0 revolution? Well, it's better to first start by thinking about what's quantum 1.0 revolution. So the electronics that we use every day in our lives, it's thanks to that revolution. So semiconductors allow me to use this computer, the internet, lots of different devices. As you can see from these pictures here, I've displayed at the top right, this is a lattice structure of what a semiconductor looks like. So it's based out of silicon atoms, and then to help the lattice conduct electricity, you dope the material with another type of atom, in this case, phosphorus. So these semiconductors were then, we could dope them with different materials and then create these things called transistors. And the transistors obviously replaced vacuum tubes. And so now we have portable devices, we have our phones and things like that. That's all part of that quantum 1.0 revolution. Also, you might be familiar with LCD screens and LED screens. So LEDs are light emitting diodes, and this is a picture of a common set of colors that you would get. Other types of displays, so liquid crystal displays, LCD, that's another type of quantum 1.0 technology. Lasers, so a laser is light amplification by stimulated emission of radiation. That was actually invented in 1960. We use lasers in lots of different applications now. For example, barcode scanners in stores, speed radar guns, LiDAR detection, the internet, like how I'm streaming to you live right now. So fiber optic cables. Also precision manufacturing. So if you want to cut through very, very thick material like metals, or very dense materials like a diamond, you can now use high-powered lasers for that. Also healthcare and beauty. There's lots of applications in medical science and also just in the health and wellness sector. So another form of quantum 1.0 would be the wireless and broadcasting technology and also inter-satellite communication. So using different portions of the electromagnetic spectrum to transmit information. So you'd be familiar with radio waves. This diagram here is showing the full electromagnetic spectrum from radio waves to microwaves, infrared. So that would be the color of light we use for the internet. And then we have X-rays, gamma rays. These are the types of photons that we use in our medical science. So here, one more example of quantum 1.0 are all the different examinations you can do in using different types of light or different types of quantum physics. So X-rays we're very familiar with. MRIs, that's magnetic resonance imaging. So it's using the magnetic moments of the protons in the water molecules inside your body to detect diseased tissue. And you can see a sample MRI scan here on the left. There's also medical exams that use antimatter. I bet you didn't know that. So a PET scan is a positron emission tomography. This is a medical exam that can be used to detect disease in organs and tissue. And you, by administering a radionuclide to your patient, and then that goes into the particular organ that you want to study. The nuclide will decay. That decay process will release positrons. Positrons are antimatter. They're the antiparticle of an electron. So particles and antiparticles, they like to be as close as possible, and they will annihilate instantaneously and create a photon. So as these positrons are being emitted, they will interact with the electrons immediately in their vicinity, create these annihilation photons, and then this PET scanner has all of these detectors around your body to measure these photon events. And then you can reconstruct a three-dimensional image of your body. So that's quantum 1.0, also very, very relevant in our lives. So what is quantum 2.0? So this is technologies that are using quantum properties and materials to do a task. So that could be computing, sensing, or secure communication, just to give a few of the main examples that we hear about. So for computing, we often hear about a qubit, a quantum bit. So I wanted to just show what is that. So in this picture here, we're showing an atom that has a spin. You can see on the top it has spin up, or at the bottom of the block sphere, which is this sphere in the middle here, it would be spin down. So these are the two configurations that the spin can have. Now in quantum physics, we have the superposition principle. And until you measure the spin is going to be precessing and oscillating and having a superposition of either spin up or spin down. And you can control how the spin precesses by applying a particular type of magnetic field. And also you can use laser pulses to manipulate this qubit, this atom. And by making spin up mean 0, for example, as a bit number, and spin down meaning 1, then you can create information stored in an atom, qubit. So I want to go through some other examples of quantum technologies from 2.0. So as I said, this is how you store information in an atom or a photon. A photon is a particle of light. Classical computers, as we know, they store information in these individual bits that can be either 0 or a 1. Quantum computers use qubits to store the information, and because they can have that superposition principle, it can be in a 0 and 1 state. Qubits can also interact and work together to solve problems. And this is very unique that a classical bit and classical computer cannot do. These special properties allow quantum computers to potentially solve problems faster and possibly more efficiently than a classical computer. We're only going to know how well these quantum computers operate when we actually have the real systems in place operating. Currently, there are what's called noisy qubits, and we do have companies that are making quantum systems that can perform computations and optimization algorithms. So there are these systems that we're testing now. However, they're not fully universal quantum computers just yet. When we do have that, then we'll be able to test other algorithms, like, for example, Shor's algorithm and Grover search. So these are particular types of quantum algorithms that are expected to perform much better on a quantum computer and than a classical computer. And in particular, Shor's algorithm, which I'll mention later, is the one that can potentially hack the RSA code that everyone has been talking about, that quantum computers could potentially make vulnerable. So for a few different examples of quantum computing platforms, I just wanted to give a few images here and talk a little bit about it. There's many, many different platforms, and I do not have enough time to talk about them all. That would be its own hour talk. But here's a few examples. So we have atoms and ions. As I already mentioned, we can manipulate the spin, and we can assign spin up and spin down as a 0 and a 1. We can also do that with energy transition levels that are inside the atom. That's how some of these atomic memories work. And if you want to know more, I can always talk about that later. We have photons, as I was mentioning. So those are individual packets of light. Now, encoding the 0s and 1s in light is very interesting because we have lots of different parameters to play with. We have color, polarization, time bin, so that's time of arrival of the single photons at your detector. Also spatial modes. So the image you see here on the right is a photonic circuit where the light is interfering at various junctions, And because light doesn't like to talk to each other, think of two flashlights. If you were to shine two flashlights at each other, the light just passes straight through. So when we want the qubits to interact with each other, in the case of light, we need to put some sort of nonlinear medium in there. So that's what these intersection points with the various ETAs represent. Then here, we also have a diagram on the left showing superconducting circuits. So this is a different type of qubit. It's a microwave cavity, and there's a qubit inside that microwave cavity, and then you interact using microwave radiation. And the actual circuit is shown in this picture B. So you can see the squiggly lines. That's the actual cavity of the microwave resonator. And then the pictures below shows a micrograph of the material that the Josephson junctions are made out of. So this is the actual manufacturing. This is the quantum materials that AJ was talking about before. So that was a brief look at quantum computing. Another form of quantum technology I mentioned is quantum sensing. So you might have heard of the recent discovery about the gravitational waves by LIGO. So this was the idea that if there was a massive event in space-time, there would be a disturbance, and then the ripples would cause space-time to literally ripple like you see here in this image, like ripples on a pond. And then if you had a very, very, very long interferometer, I used to work on interferometers in my lab, and the path lengths were on the orders of centimeters. The path lengths here are 4 kilometers each arm. I cannot imagine aligning that. So you have also they're perpendicular, ones going in a right angle to the other. So the reason for this is because if a massive event were to happen, hopefully one arm would be affected differently from the other. That difference would allow them to measure that there was been a disturbance in space-time, and they would be able to detect a gravitational wave. However, this is a very, very sensitive measurement to do. And so one of the technologies that they implemented to help with reducing the sensitivity and improve the synchronization of the detections was to reduce the quantum noise by using entangled photons and squeezed light. So I haven't really mentioned entanglement yet. It's basically a correlation that exists between two particles. Either they're two particles of light or two particles of matter. And this correlation can be harnessed to, in this case, reduce the quantum noise that exists. Everything in the universe has a base level of noise. It's like a quantum foam. It's always there. But you can play tricks, and you can kind of make it look less noisy if you look at the light in a particular way. So there's always Heisenberg uncertainty principle. So you might have heard of that before. If not, don't worry, you don't have to. But it's that trade-off between position and momentum. So in quantum physics, the trade-off between position and momentum, the faster something is going, the less you know where it is. Makes sense? And the more you know where it is, the less you know how fast it's going. That one doesn't make much sense. But when I explain it with diagrams, it makes sense. So in this case, we're talking about phase and amplitude. That's our position and momentum of light. And so they squeeze some of the noise out of position, phase, for example, and that means a little bit more noise goes into the other one, but that's okay because we just want to use one of those quadratures for the measurement. So because they did all of these things along with lots of different other technologies to stabilize these interferometers, they were able to measure gravitational waves. And then a third aspect is that quantum secure communication. So AJ was mentioning how important data security is. And public key encryption is based off of factorizing large numbers. RSA code is based off of factorizing large numbers, which is very difficult for classical computers. But it might be easier for a quantum computer thanks to Shor's algorithm, for example. And so we've known this for a while. Shor's algorithm has been around since 80s or 90s. And so the community has been working on quantum key distribution, QKD, and also post-quantum cryptography as ways to mitigate this potential threat. In terms of QKD, it's not the encryption is not based off of solving harder math problems. It's actually a physical process. You are creating an encryption key between two parties, and you see the parties here in this picture, Alice and Bob. And this encryption key has theoretically 100% secure. And then if you use it with your one-time pad encryption, then that message cannot be hacked, because you can only hack that message if you have that particular key. And so as long as that key is only shared between Alice and Bob, and thanks to quantum physics, if an adversary, Eve, tried to intercept your key while you were generating it, because it gets, as you see here in this image, the quantum channels going from Alice, who has a laser, to Bob that has detectors. So if there were somebody in the channel trying to intercept your key and disturb your system, they cannot copy the information, because quantum information cannot be copied. They also would disturb the system, because measurement disturbs the state or the system. So you would know if an adversary was trying to tap into your key. And there's a certain threshold of noise that we can tolerate. And so once that key has been generated and you use it once in your one-time pad encryption, that is a theoretically 100% secure encryption method. That is not something that you can say about a lot of encryption today. And the other wonderful thing is that if it is secure today, it'll remain secure tomorrow and into the future against any advances in computing power. So as we mentioned, we are the co-founders of Qubo Consulting Corp. These types of topics are the types of topics that we are helping businesses, organizations, and investors understand, so that they can make better decisions about what quantum industry is and what this new tech is that's coming out. So we offer quantum training, as I mentioned. We also offer coaching for startups. So this is helping startups and science communicators reach their target audience through technical education and sales. And if you'd like to know more about the Qubo way of education, you can ask AJ later. We also provide technical due diligence. As I mentioned, I have 15 years experience in quantum physics, and I'm now actively doing technical due diligence on quantum technology. So if you're interested in that, please contact us. There's also this Canada Job Grant that might be of interest to you. And it varies by province. In Alberta, in particular, the government will contribute 2/3 of the training cost, up to $10,000. So there's the website if you'd like to learn more. And just a quick overview of the types of quantum training courses that we offer. As you see, it's a leveled system with prerequisites to progress to the next level. Obviously, these concepts, as you can see, can be complicated. However, these modules are targeted for people that have zero technical experience, or if you're interested in a more technical education, we offer that as well. So if you have any questions, please check out our website, and I will go through the summary. And I don't know if you want me to go back to your summary.
No, I think you got it.
Okay, so as you've now heard, society has already experienced quantum 1.0 revolution, and 2.0 is coming next. And in some cases, it's already started. Quantum technologies use quantum properties and materials to do tasks like computing, sensing, and secure communication. There are many possible applications of quantum technologies, and it's key that the business needs are met with their quantum solution counterparts. As I've explained in very brief detail, though, information can be stored in individual qubits where the value exists in that superposition state of 0 and 1 until it's measured. And we can harness that property for quantum computation, as I've mentioned. And as AJ was mentioning, Q-Day is coming in the next 5 to 15 years is the industry prediction currently. So starting to get quantum ready now is very important. Think about what your transition time is for your organization, because training is key, not only to help your business, but also to help transition the workforce, because now everyone is going to need to get quantum ready. And if you'd like to learn more, please check out our website. Thank you very much for your attention.
Thank you so much, Katanya and AJ. Really appreciate the presentation there. Also, I think I want to say, just with regards to the Q Day, we talk about things being like 5 to 10 years, but things like the explosion in AI and other technology show that things usually come sooner than we expect them to, even from professional fields.
Exactly.
I'd like to open it up to questions. Tanya, do you want to take down your slide if we just go into Q&A just to allow people on the recording to see? Cool, that's good. I see a few people have their cameras off. So if anyone has a question, feel free to raise your hand. The raise hand button should be on the bottom bar. It's usually hidden underneath reactions. You could also throw your question in chat. I do have one from earlier that Angela put in chat asking, do you do research with graphene? I think that was specific to looking at the processors and some of the architecture that you were discussing there.
Sorry, we were trying to unmute.
No worries.
Did you say that the question is in the chat?
Yeah, it was in the chat. So Angela asked, do you do research with graphene? That came up when you were talking about the slide with the different materials.
I see. So I don't personally do research with graphene, but I do know of research done with graphene. My specialty is quantum optics, so generating non-classical states of light using nonlinear mediums like purely cold lithium niobate crystals.
Very cool. I think Angela also had a follow-up in the chat, and I
How to
see
get
they have
access.
qubit sense on there, asking, yeah, how to access equipment. I guess like accessing that for this is probably building more of the quantum systems.
Right. So
yeah, go ahead.
some of those some of that equipment is specialized and would require like cryogenics and a lab with optical cavity setups. So, but some of it is you can purchase it and have like a tabletop version. It depends. There's a few different companies that offer. I would look in for optical tweezers and for spectroscopy items. I would look at like Thor Labs, a company like that, just to get started. Because you Google something like that, and then all these other ones come up.
Mm-hmm.
Yeah.
Thank you. Peter, you got your hand up there?
Okay, cool. Yeah. No, I was just wondering about any recent developments with the big quantum computer manufacturers, because most of what I Google for the past 2 years seems to be like revenue reports and stuff. I was following D-Wave for a long time, and like they talked pretty concretely about their new architecture, but that paper is like 2 years old now. Like, just what have you heard? Because it seems like there's nothing super like getting posted from the large manufacturers.
The latest I've heard was IBM Quantum announced their new roadmap, and they were pretty excited about that. I'm not really a technical expert, but they definitely have a progression of how many qubits. I think I can't remember what they're at now, 144 or something like that on their newest system. I think it's called Heron. They're all named after birds, so I really like it because I'm a bird nerd. But yeah, I think they're planning like big things around like 2029, 2020 or 2030. And that's when they kind of expect like that's when the really like exponential growth will start to happen with quantum computing.
Yeah, and a lot of companies are definitely holding back, and they're not going to publish the latest and greatest of what they've achieved. So we know for a fact, we've talked with people in the industry who were like all smiley, but they didn't want to say anything because they had to wait 6 months before it was officially released. But some of the big milestones are getting through error correction codes and the scalability factors, making the noisy qubits less noisy. Because right now, even though you have 100 qubits, they're not necessarily useful. So things like that. So we're still there's still a few technology bottlenecks that I think that the industry is working on.
All right, thanks.
Keith, you got
Welcome.
your
And-
hand up there? Oh, sorry. Go ahead, AJ. You have something to add?
I want to address the question in the chat there by Eva. Do you have credentialing badging for courses that employers would recognize? So excellent question. We're actually looking into this right now because we do have our first client. And so we told them that we would do badges. And so now we have to figure out how to do it. But yes, we're definitely going to offer badges of some kind. I'm looking at how to get them added to LinkedIn so that it would be like, oh, we completed Quantum 101, the basics. We completed Quantum 102, the revolution, or whatever the course that they take would be. And hopefully, we kind of garner a bit of a reputation and figure out, our position in the marketplace, and people would start to recognize us and recognize our business and recognize those badges then. And I think they're all going to grow together as our business develops and progresses. So thank you for that question. But yeah, the answer is yes, we have badges.
Yes.
I don't actually have them yet, but we will.
Well, let's chat. I put my contacts in the chat to you directly to Katanya's.
Yeah, I see it there. Thank you. I'll send you a message after the meeting.
Sounds good.
Yeah, I've talked to Eva a couple of times. She's well involved with the education sector. So thank you, Eva.
Hey, it's good to see you again.
I think I saw a hand up there, but I think that went
Where
down.
was it?
I think that
Thank
was
you,
Keith's
Jerry, for
hand
your
up.
support.
Keith, yeah.
Yeah, I'll throw in. Thanks, Ross, for finagling me into this one. And Katanya, my son was a quantum physics university student, so thank you for being as baffling. It's always wonderful to be just absolutely baffled by quantum physics. But
Thank you.
the point, or at least the provocative nature of the description, is to discuss the economics of, and Ross shut me down if that's the next presenter's job. But are we using economics in like the academic term, or are we using economics in like the fiscal and how it impacts the way exchanges of money and capital, et cetera, goes? Because I think both are pertinent. And it was funny that it's no doom and gloom, but 100% half of your presentation was how we are currently up against an encryption problem right around the world, and we've got a classical encryption problem that has left a municipal medical center as they've been held up by ransomware, and now they've gone completely back to paper because they haven't been able to get around that. So I 100% think that there's going to be some much, much bigger encryption related concerns that we're given any credit to. Like I was a kid when the IBM PC Junior was a thing, and you could get one in your house, and you wouldn't want to open this and touch that button, or write in this little piece here because that'll make your machine go, it'll brick your machine. I think we're going to get a lot of bricked stuff right around the world once a little bit of unbridled AI coupled with a computational capacity of some of these Q machines. It's going to be pretty wild. But yeah, so sorry, back to the question. Are we going to be on the economics as a checks and balances, academic, full cross spectrum thing, or should we talk about money, or what are we going to do?
So yeah, I'll talk to this. Yeah, I think I'm not sure I understand the segregation, but what we're projecting, or what we believe is going to happen, is that these technologies are going to be disruptive, like all across the economy, and have implications throughout every industry as we kind of present it. And so what that means is that there's going to be new challenges, but there's also going to be new opportunities as well for businesses to get positioned, to gain a competitive advantage and be prepared for this. Because, as I mentioned, the transition time, and I just said the cryptography thing, right? Like if it takes you 20 years to implement a new cryptographic standard in your organization, then like you should have started planning 15 years ago. But I think in other industries as well, like it's going to be important for people to adopt and try. And me being an educator in a former life, I believe that there's value just in knowing about it and trying something new and seeing what happens, and playing with those, big, I think you call them brick computers or whatever. I think playing with those will put people in a good position to take advantage when the time is right. And, I agree, like the general consensus across business and industry is like, well, show me the quantum advantage. And it's like, well, yeah, like we're kind of there. There might be like a little bit of an advantage at this point in time, but we know, or we predict at least, that it's going to become a greater and greater advantage as time goes on. And so I think that the best thing a business could do is to try a new technology, and position yourself so that you're ready to adopt when the time is right.
Totally agree. Advantage, absolutely. I mean, this is going to be advantageous to a great number of sectors of society, but similarly, it's also going to be disadvantageous in the very same way that the progress of computer technologies is happening today. I'm an older tech guy. Last time I had a real job, I was an ERP analyst in a manufacturing company in Calgary. So I have had some computer experience, but I also recognize that a great number of the people who are out there, they're not getting the kind of training that allows them to even begin to have those conversations about, what is it that I need to learn about this? How will it impact my job on a daily basis? I do think that there's going to be a lot of people who are going to be absolutely blown away, left in the dust when computing gets even better. I do think that there needs to be a whole lot greater consideration, like full cross spectrum, about how it is that society, and when we talk about economics in an academic term, how it is that society is going to brace itself for in an even greater disparity between intellectual capacity of its societal members. So, sorry to veer away from the computer stuff, because I mean, this is mad computer stuff. It's great, but there's a huge social impact involved with this.
Yeah, definitely. And I know there's lots of people looking at, standardization, equal access to things like this. And so there's a big challenge going forward to try to produce that, right?
I think I want to chime in because I have a couple of interesting facts when we're talking about the actual applications of quantum computing. And one of the things that I heard about with the conference that I met both of you at was how LA's port was able to increase their capacity by using a quantum computer. So there are large organizations that are already using these major quantum computers that are held by the tech giants currently, like IBM and Google and Microsoft and Amazon. I'm going to drop the link to the PDF that D-Wave published about it, that just talks about it. But it's basically the logistics of processing where those shipping containers are going and what they're doing. If you process that and front-end it into a quantum computer, you can improve the efficiency versus having a classical computer try to brute force the best solution to it, or people just haphazardly moving containers inside of the giant shipping area. And that's large scale, but feasibly, like looking at your presentation, you were talking about different areas of different sectors. You could apply that quantum computing to those different sectors. And even as we move toward that, like quantum cryptography, as much as that's something that we need to be wary of, and kind of Keith talked about, we're already seeing the benefits of quantum computing being used by large organizations. And as that cost comes down, and then as we increase the quantum computing technology, there will be more of those opportunities. I think the closest comparison I heard, and feel free to chime in on this, Tanya and AJ, but like we're now at the quantum period, probably to what classical computers were in about the 60s and 70s, like mainframe type access. But then feasibly we'll probably reach that point where it'll be smaller and probably like more of an on-prem type system within a number of years as we're starting to standardize that hardware. Yeah.
I feel like we're at the point now where, yeah, quantum computers are going to take up a whole room, right? We don't have a laptop or whatever to put them on. But the other thing to keep in mind is like quantum computers likely won't replace classical computers. I don't think classical computers will ever go away. It'll probably just be more integrated with a quantum system.
And that's one thing is like the comparison that I've heard is like the quantum computers are not literally but figuratively the way they work with a computer is kind of like a graphics card works in a computer. It's a separate add-on that's still connecting into the classical computation system, but we're also in the stage of being able to design how those are interacting with one another, because it's kind of the social development of technology as well, right?
Yeah, and you also have to code in a quantum language for the quantum computer as well. So it's like people are going to learn new coding software as well. So it's not just a hardware link, it'll also be a software.
This connects a little bit to one of the questions in chat that Mike put in, and I'll get to in a second, Keith. But Mike asked, what jobs are your courses catering to? Mike mentioned that he did a quick search on quantum job opportunities, and most of it right now looks like research positions. But if you could talk about kind of what your courses are catering to and what you're seeing in the market.
Well, okay, so we have plans to make upskilling courses. Right now our courses are designed for like C-suite and upper management, the decision makers, government agencies, as well as investors. But I do want to get into training the workforce. How do we upskill the workforce? And with Katanya's background, I would just guess that we would probably start with photonics.
But in terms of like, I know if you just Google the quantum jobs, you're right. Most of the current positions being advertised are for at least undergrad or higher. But that's not going to be the case for the next 5 to 10 years. There's companies now, for example, cryogenic companies that need tradespeople. And so I think it's only 1/3 of their workforce have PhDs and are quantum physicists. The other 2/3 are various tradespeople. So that's what I mean by, that's what we mean by the quantum, there's going to be a quantum workforce.
Yeah, and you're talking about like the technology to build like the chiller systems and all that
yes.
run these quantum computers, because you need to be able to have all of that server room size hardware just to cool that little bit that's doing that quantum processing.
Yeah, and if I showed you a picture of my optics table from my PhD work where I was making, you know, one of these little quantum bits with photonics, it fills the entire room, right? So we're in the stage of quantum technologies now, like what the computer was back in the 50s when it was literally filling entire warehouses and we had these tape drives and all this stuff, right? So we're miniaturizing it a lot, photonic chips going down to waveguides. You're able to put a quantum source, your gates, your detector, all on one little fiber coupled chip. That's amazing. That used to be my entire table. So eventually, but now we've got these superconducting circuits and we have these atom optics. They require cryogenics sometimes and vacuum systems. So it just becomes very cumbersome. But as we figure out how to miniaturize and the technology evolves, but as AJ said, it's most likely not everyone's going to need a quantum computer. I kind of make this analogy. Think about it. If you have a really fancy like Ferrari, would you drive that in snow to the Rocky Mountains to go skiing? Well, if you want to go off the cliff, maybe I would take my truck, right? So a quantum computer is like a specialty tool that we want to use in certain situations where it makes sense.
No, thank you. Keith, you had your hand up. You still got another question there?
Yeah, it was actually a comment back. I put it there in the chat as well. The interesting part as you'd mentioned, Ross, like the architecture of a graphics card was a really good, for instance. It's much more particular to what it has to do. Watched a bit about the re-advent, if you will, of analog computing in building chips and computing apparatus that do specific tasks to stop the, let's call it, digital wastage of standard computer technology, where it has, like the Ferrari example is a good one. It would be the Ferrari. You're right. You're not going to drive it out to the mountains, but it's not, there's no absolutely universal way of getting things done. And because the computer technology, and actually I think Ross, you and I talked about this, that when the computer technology is as small as it can be and as cooled as it can be, the next step is to try to make it as effective in its task as can be. So with the, and as appreciating that quantum is now another technology that's different than just streamlining standard architecture that there is out there today. I'm one who's always been critical of home computing never getting to a point where it was ever a television or a radio. Home computing should have gotten there 20 years ago. It's still the Wild West. You still require considerably more knowledge than a pedestrian person in order to get your machine to work properly. I mean, look how many guys make a whole lot of money off of debricking some machines, right? If your computer goes south, most people don't know how to get back into it. Myself included, I'll mess around with it and eventually lunch the thing and throw it away and buy another one. But I'm really anxious to see how this quantum and this analog thing I found very interesting stitches in with these what you're calling classical computers. Do you think that the analog computer will be more specialized? I was sorry, the quantum computer would be more specialized. I was kind of thinking that it's going to be a replacement, I guess, if you will, for the classical computer, but you say it's going to stay. How does that work?
Well, you can see from that one of the diagrams I showed with the QKD system, you still needed a classical communication channel between Alice and Bob to finish off that protocol. And that involves like the internet and just regular computers to compare some, to do some comparison, to do some sifting. So there's lots of different schemes where you still need a normal classical computer to complete the protocol.
And maybe just mention, like, quantum computers aren't better than classical at everything.
That's right. For example, operations like addition. Those are pretty simple for a classical computer, but for a quantum computer is quite tricky. So there's going to be some operations where it'll be more computational efficient to use a classical computer over a quantum.
I didn't realize something as simple as addition is more complicated for a quantum computer when we're talking about it breaking encrypted systems.
Yeah.
Jeff,
it's just the way the bits work and everything, and the types of operations and types of gates you have to stitch together.
Yeah, that's fascinating. Jeff, you've got your hand up there for a question as well.
Yeah, just a couple questions. The the first is regarding the sort of combination of emerging technologies, and whether how quantum might fit into the picture. So I mean, one example would be artificial intelligence, right? And sort of the step change in AI and ML that's kind of going on right now. But if that is, can be made, let's say 100 times more powerful with a quantum engine or a quantum platform, is that kind of possible, or is that the wrong way to look at the potential role of the quantum computing?
So the difference is that AI is like not quantum at all. It's classical algorithms running on a classical computer, and so it's something that can learn, right? It's an algorithm that can learn, but it has nothing quantum about it. Whereas the quantum computer, you're actually using quantum elements to do the computing. And so it's a different platform. So a lot of people have asked me, like, what would happen when AI could be merged? Like, could it be merged with quantum? We don't know. Nobody knows. If anybody thinks that they do, I would like to talk to them, because we don't understand how it's a classical system and then it's a quantum system. So it's like, how would that even work? You'd have to code, right? You'd have to create quantum machine learning. So it's like, it's very different. So we need to explore it further, I'd say.
Yeah.
Is it kind of at a state where we still need to develop the quantum computer enough for it to be standardized to even see about trying to connect those systems and those ideas together?
Yeah, for sure. Yeah.
So probably still looking at that like 5 to 15 year window before we can even conceptualize or test what that kind of integration looks like.
Yeah, and there are people that are making simulation software to help with these things, but again, they're simulating quantum things on a classical hardware. So it's still an approximation.
It's like trying to simulate flying through driving.
Yes.
Yeah. Jeff,
go ahead. The other question is, I really like your examples because it helps to make it real, but I'm wondering what examples you might use in the sort of the social nonprofit civic space, right? Of potential applications of quantum for social good.
Mm-hmm. How about security for the Internet of Things? So cities all around the world now have these systems deployed everywhere, and most of these systems are not encrypted, or they have very, very limited encryption, or it'll be soon legacy systems that nobody will replace. So if a quantum algorithm could help with secure the Internet of Things, I would think that would be a very common civic goal in mind.
I think what Jeff's trying to get at is like the for good. So like more the like if there's an area in humanitarian work when you're trying to provide benefit, what could a quantum system do in that sort of like human data processing, understanding things space versus just the security side of things?
That's an excellent question, and I don't have any research done on this, but I can only imagine that optimization would really help. Like I was just looking at charities the other day and trying to figure out who I'm going to donate to before the end of the year, and I'm like, hey, I'm not going to donate to those guys. They're only giving 60% of every dollar that I donate to feed the hungry or whatever the cause may be. And so with optimization, I could see them bumping those numbers up and figuring out, hey, we don't need to spend money on X, we should spend money on Y, and then more of the impact is felt by our clients. So that's just off the top of my head, though. Like I said, I haven't done any research on that.
Yeah, one area. Oh, go ahead, Katanya.
I was just thinking like early warning systems for weather. So predicting major weather occurrences, because that is a chaotic system. We currently use supercomputers to do the modeling, but it's very flawed, obviously. So potentially that could be a way.
I'm thinking of one other area I heard of, and this kind of goes to the shipping example that I gave, where companies have been using it for last mile shipping. But another example could be if you have a food waste organization and they're trying to figure out the best way to deliver people who need the food in the amount of time before it's expiring. That's a very hard problem. And if we're talking about shipping and receiving in time duration and doing it most efficiently to save the most amount of food we can, that sort of application, I think, could probably be one as well.
Yes, and those types of things are being run right now on platforms like D-Wave.
Mm-hmm. Mm-hmm. Keith, you've got another question there, and then I'm going to go to a couple of
riff. That was kind of absolutely the point. The transportation industry as a whole, when we talk about self-driving cars and things like that, one of the holdups is that the level of interaction is too great for standard computing models to be able to handle right now. And when we talk about the economics of it, in the groups that I talk about this kind of stuff with, once we get to a point where automated vehicles become a norm, and especially when you're talking about public transportation, in most municipalities, the first mile and last mile is an awful thing. So once you're on the train, it's not so bad, or the BRT. But if we can get to a point where you have, like, say, a little bug out front, you just hit your app and this thing shows up and gets you to the major route. The disruption there is now, because the safety has to be at least 100% in order for municipalities to embrace this type of technology as on a regular basis. Because it's that safe, the municipality can then underwrite all of that first mile, last mile insurance. Any claims that come down from that, because it is so safe, is now something that a municipality could pay off. The insurance industry then stops making that kind of ridiculous revenue that they make. And imagine that disruption. The counter, of course, of most of the people who I talk with, and they're reasonable people, is that people will not give up car ownership even if it's automated. So I'm an advocate for inner city transportation being completely public, with that self-driving model where, you know, you hit a button on your app, you step outside, and you have a path of where it is that you're going to go. But the insurance company is going to be totally choked when that finally hits the pavement, so to speak.
Good.
I think that's going into your finance comment from earlier there, Keith, expanding on it, because there will be a lot of areas and sectors like that. I think with the quantum side of things, a lot is like at least first processing, like that route and logistics management. I don't know about the cars themselves, because right now that's a classical computer inside the car that's doing most of the processing. But if that's miniaturized and inside of a car, perhaps if it's then still connected to the cloud network and it's getting the guidance from there and sending the information back, once we reach a quantum level of quantum computing, we could have that centralized guidance system, so to speak, for the whole various transit networks across an entire city.
And the fact that it can compute two different outcomes at the same time, which is very much a whole safety thing where everybody pushes back on computers. Computers are too direct, where, as I understand, quantum computing will be a lot more organic.
Yeah, you could say that. You'll still get one answer. You'll still with these optimization algorithms, for example, you put in parameters, you let the quantum system evolve, and then you get out an answer. So even though it is quantum and there is this superposition of zeros and ones, you still get a defined answer at the end of your calculation.
And so, yeah, you mentioned the computing power as well, but I think also quantum sensors would really come in handy in autonomous vehicles, because just being able to detect that much more specifically or clearly, or, you know, whatever you want to call it, precisely, I think would be really beneficial too.
Sounds good.
I'm just going to go into chat. Angela asked, is there any research being done on superconductors and integrating quantum and classical systems at room temperature?
Yes, there are quite a few research groups that are looking into room temperature devices. I could send you some, if you'd like to learn more, please send us a message through our website. There's a contact us page, and that's our website. Or you can Google our names, they're pretty easy to find. Yeah, and room temperature, just so everybody knows, is not requiring cryogenics. And so this is very interesting technology for working on satellites, because obviously getting a cryogenically cooled system on a satellite can be very power hungry and weight costly and also large. So yeah, there's a lot of work. There's actually quite a few research groups even in Canada and in Alberta in particular.
I'm just going to go for another question from chat. Of course, my birds are saying hello. Yeah, there they go. And I lost my place in the scroll. I did just drop your website in
Thank
chat there as
you.
well, so people can click on it there and navigate to
I
it.
see the next question from Mike Lee says, can it be used to mine Bitcoin at a rapid pace? So from my understanding, mining Bitcoin, it has to do with the computational power, like literally the electricity needed to run your computer, and whether it's more than what you'll harness out of the mining of Bitcoin, right? So I know of a couple people that have studied this for a research topic for their masters, to see if a quantum algorithm could be more efficient at mining the Bitcoin compared to a classical algorithm. I think the question is still out there. It's still an open research topic, and people are looking into it. Whether a quantum computer will be better at it, I have no idea.
Still one of those areas that remains to be seen, depending on where developments go. I don't think
We really
anyone's
need a platform to play with to know what it's capable of doing.
Mhm.
I like Mike Lee's comment. If I am rich, I will take the Ferrari. He was talking about going out to the mountains. Like, he wouldn't take a Ferrari.
Yeah.
Then he said they make snow tires for Ferraris.
Yeah, I think it depends on your weather conditions, and I think there's only so much snow tires can do with a vehicle that goes at that level of speed for the most part.
And low to the ground, right? I'm thinking of like roads that aren't plowed. It's like
Yeah, sometimes those Ferraris even have trouble getting in and out of parking lots with how low they are, aren't they? Like there's one area that I saw where the road like dipped up and the sidewalk went down, and even regular bumpers were scraping against it.
yeah,
Oh, yeah.
not good.
Brent is asking or thinking maybe a quantum computer could compute human walking probability as in where they step on the road. Like, I don't know I guess if we're talking about transportation logistics and where people are going, perhaps that as well.
Yeah, there's also something called quantum random walks, and you can use that to predict the way a drunk person would walk down the street.
Wait, so you can predict how the drunk person would walk, like the variation and where they're going and like where they will end up stumbling?
Yeah. I think Richard Feynman was just like a very quirky person, and he, contributed to this theory. And yeah, so I learned this in my undergrad. So there's a correlation. You can use quantum random walk as a predictor for how a drunk person would walk.
Is it that the quantum system is acting like how the drunk person walks, or is
Yeah,
it
it's a system that's based off of probabilistic choices, and then there's like a weighting to the probability. It's the same kind of idea. If you were to shoot a basketball at a hoop, right? Classically, that basketball does the parabola, goes straight. It doesn't deviate in some weird angles or anything, right? But in the quantum world, if you were to shrink down, you shoot the ball, all of a sudden, as soon as you're not observing it, say you close your eyes, you're not observing it anymore. It could be everywhere at once, right? Its position could be anywhere. It's only when you open your eyes and you look where it went, that's when you know. So, but it would have a probability distribution. It would be most likely going to go straight ahead, most likely going to go over the side. But there's going to be this infinitely small, but still there, probability that it went straight behind you and smacked somebody in the face.
I think this actually ties nicely into Chris's question in chat. Chris saying, trying to wrap my head around quantum computing and it having difficulty doing addition, but quantum computing, I guess, is it more abstract thinking or logical thinking by the way to look at it?
Oh, about how it actually has to do with how the operation is implemented using the qubits. So it's a little bit more complicated. I would need to break out some math, but it has to do with the physical implementation of the algorithm on a quantum computer.
Keith, you've got your hand up for another one there.
So, but a huge amount of more variables. Like the reason why I can predict where the drunk person is going to walk is it leaves a whole bunch of computations open and then begins to answer them to finally get, like you said, to one final answer. But that one final answer repeats over and over every nanosecond to give you an idea of where that thing is. So, I mean, it's turning gray into black and white, there is always an answer. Do we have the ability to compute those answers all the time? You know, our brains do a pretty good job of it, and then a pretty good job of compartmentalizing what it needs to spend its energy on. Yeah, I hate to riff on that car stuff again, but if we ever got to that point in a city center, you wouldn't need traffic lights. There wouldn't need to be sidewalks. You could walk wherever you wanted to, because the car that's traversing this space would be smart enough, quote unquote, to be able to not run over people and kill them and still get to their destinations.
Mm-hmm. Yeah, and they are looking into quantum sensors as a better. So, for example, there's a lot of obstructions like weather. So fog detection in fog is very difficult because the water molecules bounce our radar signals back at us sometimes. And so if there's a quantum sensor that could cut through the fog by using entangled photons, because maybe that will help reduce some of this decorrelation that happens from the presence of the fog, that could be another way to help. So it's a lot of active research topics right now.
Yeah, and a subroutine that recognizes that it needs to not go faster than this velocity because it can only take in this much and braking distance is this far.
Yes. Lots of humans don't seem to understand that, as I keep yelling at them. We cannot exist in the same physical space. Pauli's exclusion principle says it.
Yeah, sometimes people get a little bit too close in traffic, like even how close some people get to pedestrians. I swear they're just flying by the sensors in the front of the car rather than actually looking out in front of the car these days sometimes.
Yeah.
Do we have, I know we've been having a really great discussion and there's been a lot of really interesting questions, which I appreciate. I'm just trying to see, is that another question in chat though?
So
So,
Brett's asking about invisible bombers and things like that. So there's definitely you can Google this. It's called ghost imaging. It's a technique to image something using entangled photons where you don't necessarily have to interact, like one photon interacts with the object and one doesn't. And then there's also ways that you can use light to make things look invisible. So that's using like what's it called? Transparency. It's like a transparency window of the atom. It's very particular. So there's certain materials that you can make, and then at a particular way that it's orientated, all of a sudden it becomes invisible. So there are metamaterials that people are looking into. But if a quantum sensor was trying to find it, it just depends, right? Like it depends what technology is making it invisible, and would that other technology be able to detect it? So it's a complicated question. But good question. I like this.
so I guess it's kind of like if you close your eyes, you can't feel smoke in the air necessarily unless it's very thick. But if you open your eyes, you can see it, sensor matching whatever the material is you're trying to detect.
Exactly. Yeah.
Cool.
Interesting. Great questions, guys. Thanks so much. If there are any more, get them in now.
Last chance, and then I'll cut off the recording, and then we'll enter more of the casual discussion time.
Just
So
one question, is quantum being used by NASA and SpaceX?
You're the technical expert.
So companies like Google and Amazon, I know, have quantum divisions. SpaceX, I'd be very surprised if Elon didn't have some sort of quantum division, but I don't know off the top of my head. And NASA is part, so JPL, the Jet Propulsion Laboratory, is part of NASA, and they are members of the KeySat International Science Team, which I'm the science team coordinator. So there's a Canadian science team for the KeySat mission and an international team. And so we are going to do potentially experiments with JPL and our satellite, which is going to be owned and operated by the Canadian Space Agency. And then there'll be a ground station at the CSA headquarters and also a ground station in Waterloo at IQC. So we might do a QKD key exchange between JPL and maybe the CSA or IQC ground station. So yes, NASA is definitely involved in quantum. They also have like the quantum, oh, what's it called? It's the Lunar Gateway. That's what it's called. And it's about satellites that will orbit the moon. They're going to integrate potentially quantum technologies onto these satellites. They want to do a moon to Earth entanglement distribution experiment, which is so cool. So why it's cool? Okay, so quantum physics, the physics of the tiny, right? These entanglement distribution experiments that we've done so far, when we involve a satellite, we've gone now over like China with Nishia's satellite, 1,400 kilometers. So they measured quantum entanglement, maintaining that correlation over 1,400 kilometers. So that's a quantum effect over macro scales. So what happens if it's galactic scales, if it's Earth to moon? So will it hold? So this is very, very interesting. These are the types of experiments that let us try to come up with the math to unite quantum physics and general relativity. So yes, NASA is definitely part of it.
That's really cool because they are trying to launch a new vehicle on their most recent rocket to do surveillance similar to the web, the web satellite. So that's but this one is motorized, so it can actually has propulsion. So who knows where it will be? That's why my question on interplanetary travel and probability simulation.
Oh, I see. It's very possible that they could use quantum algorithms to help with some of those calculations. Yeah, because they definitely use supercomputers to do all those calculations now. So
yeah. Well, very interesting. Cool stuff. Thanks very much.
Thank you, Eva. We'll be in touch soon.
Okay. See you soon. Thanks, Ross, for a great session. I've got to run.
Thanks,
so,
Eva.
See you guys soon. Okay, bye-bye.
I think Keith has a clarifying question there. Are you talking about proving atomic pairing distances?
I was talking about where they have two photons that are entangled, and they shared one with one ground station, one with the other ground station. The source was on satellite, and they distributed the photons with two telescopes. And then those ground stations did their measurements and found that the photons did indeed show correlation and entanglement. So it wasn't with an atomic system. It was with a photonic one.
Yeah, I had the wrong phrase. That's what I was wondering about, the entanglement and the distances and proving the effective distances, and because theoretically it's infinite.
Yeah. Yeah, theoretically it's infinite. So as we test it further and further, we determine, oh, look, it is still infinite.
Are there any applications to that sort of maintenance of quantum effect over that kind of distance?
Like ghost imaging or something.
Yeah, I would say ghost imaging would be a good one. You don't have to have entanglement to do QKD, but it does allow you to do untrusted node QKD. So the satellite in the middle, even if it never knows the key, so even if it got hacked, you wouldn't be vulnerable. So there's quite a few, and sensing applications. So there's to improve the resolution of telescopes, you can use entangled photons to reduce the noise, similar to what I was talking about with LIGO. So you might be able to detect, fainter galaxies or something based off of it's called very long baseline interferometry.
Okay, that's really cool. All right.
There's like so many more, but I'm tired. I'm sorry.
Oh no, that's fair. I know it's getting a little bit later. We've had a really good discussion. I think I'm going to cut it there because we're at about an hour and a half mark now. So thank you so much for everybody for being so engaged. I know a few people had to drop off already. Really appreciate the good presentation. Thank you, Katanya. Thank you, AJ. Thank you, everybody, for the great comments and questions. Really excited and happy to see people turning out and really turning the gears in the brain for some interesting questions and thought-provoking pieces. Anything last from you, Katanya and AJ, before we close out the recording for the evening?
Do I have anything? No, I don't
No?
know. Yeah, I really appreciate you guys putting on this talk and inviting us to come speak. It was great meeting you at the conference there at Q Connect, Ross. And there's another one coming up. It's more of a technical conference, but Quantum Days Canada is going to be here in February. So any, technical quantum people who want to check that out.
Yeah, and so thank you so much to CivicTechYYC, and we look forward to making more connections from this talk.
Awesome. Thank you so much. I dropped the link as well to that Quantum Days page into the chat there if anybody is interested at looking and attending that conference next year. Thank you again.
And great
so
questions.
much.
Great questions tonight. Thank you.
Yes, thank you so much, everybody. Thank you so much for those of you catching it on the recording. I'm going to put some of those links into the comments and chat there. Again, really appreciate it and hope to see you all next time.